She's one of Purcell's students.
Really?
The coach now?
Yeah, she was.
Yeah, that's pretty cool. All right, so we're looking at our heating curve again. All right, so you need to add some stuff here. So the length of the line right here, the length of the line is proportional to the heat of vaporization. Let me make this bigger so you can see what I'm writing. The length of the line, oh, there we go, is proportional to the heat of vaporization. So different substances are going to have different lengths of lines here. How much energy does it take to change it to a gas? The longer this line is, the more energy it takes. What that means is if it takes more energy to change it to a gas, it means there are more IMFs. Yes? If it's a short line, it means, hey, there weren't any IMFs there. It was easy to change it to a gas. Hardly any energy at all was taken. So the longer the line, just spit on my paper. So the longer the line, the stronger the IMFs. Okay, that's a big deal there. Now this would be where heat of vaporization is. If we go back down to the other flat line, that would be where the heat of fusion is. So here on this line, let me move it here so you can see that. Here on this line, the length of the line is proportional to the heat of fusion. How much energy? The more energy needed means a longer line, the greater the IMFs. And when I say more IMFs, I'm going to say, I shouldn't say more, I should say stronger IMFs. Okay, again, when we say IMFs, we're talking about molecules, covalent compounds, right? Not ionic compounds. So intermolecular forces are not in the whole category when we talk about ionic compounds. You understand? That's a little weird. Okay. Uriel's gotten a lot weirder without you, Caitlin. What are you doing? Okay. So the lengths of these lines matter. Even the slope of the line talks about how quickly it's changing temperature. The higher the slope means it's changing temperature faster, right? Yes? Here's your temperature along the, here's your temperature here. The sharper the angle, the faster it's changing temperature. It's heat absorbed over time. How much heat is being absorbed over time? Okay? So we talk about, and do you remember talking about specific heat capacity, specific heat? How quickly does something change temperature? So the metal on your chair, put your hand on the metal on your chair. Yeah? It feels cold, yes?
Right.
Now put the same hand on the top of your chair. Which is colder?
The metal.
The metal is, they're the same temperature. They are the exact same temperature. They've been in this room all year long, same temperature.
Well,
why do they feel differently?
Because the seat is not good conductors.
Get the thermometer.
Okay, they feel different because it's the transfer of heat. The metal changes temperature as a lower specific heat, so it absorbs the heat from your body faster, so we feel it as colder.
But
The plastic has a higher specific heat. It doesn't change temperature as fast, and so it doesn't absorb the heat from you as quickly, and so we don't feel it as being cold. Now, our hand is a crappy thermometer, but that's why. So when we talk about this slope of this line here, we're really talking about the specific heat. How quickly or how slowly does it absorb heat or absorb energy
And
from
we're
that?
sitting on it too.
Yes?
Yeah. So our weight makes it.
No. Stop there. Stop it. Stop the madness. No.
So, can that explain why when you're holding M&Ms, they just go
They have a low specific heat, which means that they change energy quickly. Chocolate does.
Yeah.
So when you hold those M&Ms or the chocolate, it starts to melt. It's got a really low specific heat. It absorbs heat quickly, and it has a really low melting point too. Can't you smell chocolate?
Yes.
Oh my gosh, I get chocolate. I always ask for chocolate for Christmas. So the first thing I do when I get a Christmas package is I smell it, because you could smell chocolate. You know, if it's the good chocolate, you can usually smell it. It vaporizes easily, right? Is it flammable? Yes, but who would burn chocolate? Yeah.
chocolate is flammable?
Yes, it is. And think about it this way. How much energy does it have?
A lot.
Yeah, you get a lot of calories, energy, calories,
yeah.
kilojoules.
Sugar.
Calories is one version of a way of measuring energy. Kilojoules is it's measuring energy too. It's just a different unit of measurement. So calories is energy, joules or kilojoules are energy. Yeah? We're accustomed to using calories, so we are more familiar with that, even though that is a metric system thing. In reality though, in chemistry and most things we use joules or kilojoules. And then if you go into some industries, you use BTUs.
What is the
Kilocalorie.
Yeah.
So if
Yeah,
you
what is
have, that's 1,000 calories.
Oh my gosh.
So if you have a little C calorie, that's 1 calorie. The amount of heat required to raise the temperature of 1 gram of the substance 1 degree Celsius, that's what it is. If you have, and this is where they're sneaky on the backs of packages, if it's a capital C calorie, that's 1,000 calories.
So, if you consume a lot of K calories, that adds to your body mass,
Yeah.
making your seat warmer.
Yes, but not changing the specific heat, that's heat.
Ha! It's chemistry. Boom. Solved it.
Yeah.
Science from like office science.
Yeah, so when you look at this, notice they're sneaky. Capital C calories. Yeah? Capital C calories, not the lowercase c calories. So on most of our foods, we're actually talking about kilocalories. They just don't like to say it. It's, instead of saying 240 calories, it's 240,000 calories. That sounds a lot worse, doesn't it? So somebody said, let's just call it 240. Yeah. So, but what we need in 2,000 a day, that's 2,000. So yeah. All right. So when we talk about these things, I just lost my page. There it is. So again, this is heat absorbed over time. The angle of the slope. I know that's redundant. Is related to the specific heat. And every substance has its own specific heat. We compare a lot of things to water. The specific heat for water is like 4.18 joule over gram degree Celsius. That's one of those numbers that you're going to use a lot in your calculations, so you might as well get accustomed to it. But specific heat is how quickly something changes temperature. How quickly something changes temp. And low specific heat means it changes quickly. And that means it's going to be a sharp slope. High specific heat means it changes slowly. Yeah. So you have a little bit of a flatter slope. Here's the deal. If this is water, that's considered a flatter slope. most things have a much lower specific heat than water. And that's a capital C, by the way. Joule over gram degrees Celsius. Looks like an E. Let me fix it. Now, what you have to be careful about is this specific heat is in joules, and if your heat of fusion is in kilojoules, you've got measurements that you have to get consistent. So usually you change kilojoules to joules so everything's consistent. So pay attention, I'm telling you this now, pay attention to the units of measurement, because you'll get a mix of kilojoules and joules, and you can't do that. So you have to have everything in joules or everything in kilojoules. Generally speaking, it's easier to change it all to kilojoules, especially if you're dealing with specific heat. Now, as we're talking about this, I'm going to go ahead and jump into something else and talk about a heat sink. A heat sink is something that can hold a lot of heat. So when you look at your lab tables back here, do I need to wait a minute? No, can you listen to them right at the same time? Okay, so when you look at our lab tables back here, they are heat sinks. The lab table is made of one solid continuous slab. And so it's got a pretty low specific heat, and what that means is when you put something hot on it, it will absorb the heat quickly, and then it spreads it out. So it can take a lot of heat without itself getting really, really hot. So it's related to specific heat in that when they have heat sinks, they usually have something that's a lower specific heat, but then it's big. If it were cut up into pieces, it wouldn't be a heat sink because the heat has to have that continuous flow. When you change materials, like let's say we tiled it and we had that grout between the tiles, well, the grout is a different substance than what the tile is, right? So when it changes substances, it doesn't go, the heat doesn't flow between it easily. So when you look at all these lab tables, they're not pieced together. The big lab table is all one solid piece, and then there's a little strip of material to where it hooks onto the back of the lab table too. So there's a little bit of a strip there, but the whole, it comes in one big piece, and it does that not because it's less expensive or because it's easier. It does it specifically so that we can use it as a heat sink, because we put hot stuff on those lab tables, right? And you can put hot stuff on there and then pick it up later, and it'll be slightly warm in that little bit of spot, but it's not enough to hot. So you can take those crucibles and set it directly on the lab table. It's not going to burn the lab table. It'll leave a little mark on there, but it's not going to burn the lab table. It's going to spread that heat out so quickly that it doesn't cause any damage to it at all. So specific heat is incorporated when we talk about what material are we going to deal with the lab. Before this man-made material, they used soapstone. Soapstone. It's a really dense rock, really cool stuff. It's really dense, really heavy, and it's got a very low specific heat, but it's also a great heat sink, so it spreads that heat out. All right, so once you have this page, let's get another sheet of paper. That's page 3, by the way. Joule over gram degrees Celsius. Is that what? Yeah, degrees Celsius, yes. So this is page 3. So page 4 is going to look like this. We're going to talk about the kinetic molecular theory, but we're not going to just focus on gases. We're going to look at some other stuff. So we talked about the kinetic molecular theory of gases. Okay, so let me backtrack a little bit. Kinetic molecular theory, when it talks about gases, is talking about ideal gases, right? Gases are, the molecules are far apart compared to their volume, so we can ignore the volume. There's no IMFs, things like that. You have to know that information. However, we can also talk about the kinetic molecular theory as it pertains to other things besides gases. So this is where we're talking about the more generic kinetic molecular theory. Oh, I have to change colors. What was I thinking? Did I just pick up the same color? Why do I have 3 of these in there? Kinetic, there we go. Did we already use pink? We did. What's going on? Let's use blue. I know, it's a difficult thing. Kinetic molecular theory. Did we already use blue?
Yes.
Did we really?
Yes.
Oh, crap.
I just looked over.
Why don't I have a green?
I have green. You want green?
No, that's okay. I'll use this
Sure.
green. Okay, kinetic molecular theory. Kinetic molecular theory, Km, that's not green. Did I not pick up a green? Okay, never mind. Kinetic molecular theory, KMT.
Right here.
I'm using it like this. Yeah, vertically. So the kinetic molecular theory says all the molecules are in constant motion. If you can see this, there we go. Molecules are in constant motion. And this motion determines the phase of matter. There we go. Okay, we talked about this. Solid, they're vibrating. Liquid, they slide all over each other. Gas, they're going all over the place. That's what we're talking about here. So draw this. Draw your 3 beakers and put a solid, liquid, and a gas in there. And my gas has to have a lid, because otherwise the molecules will leave. So we have a solid, and I'm going to put little parentheses, little quotation marks, because that generally shows that it's vibrating. We have a liquid that takes the shape of the container, and they're moving all over the place with each other. And a lot of times we say a little arrow with it curved around indicates that they're moving all over the place. And then we have a gas, and the length of the arrows indicate how fast they're going. So we have solid, liquid, gas. Okay, so we start off with A solids. And we're going to do B liquids. Haven't we already done gases? They have their own unit. So we're just going to do solids and liquids here. So solids, because we spend a lot of time on gases. Solids. So we need the structure. They have, so that's what we're going to focus on. We know how they move. We know they're the strongest in IMS. We know all that. So what we're going to focus on is we're going to focus on the structure. So this is the new stuff that you need to make sure that you understand about the solids. So we have a structure that could be a crystal. So a crystal is a highly regular arrangement of atoms or molecules. Generally, it's a repeating pattern.
What's the A for?
A, solids. We're going to do B, liquids.
Oh.
Yeah, you don't have to put on it. Would it make here? There. Solids.
Thank you.
Okay. So they're highly regular arrangements of atoms. Slash molecules. And they typically have a repeating pattern. So here is a crystal formation. Now again, you can cut it so that it has shows the light a little better, but this would be a diamond. And it's just got that highly repetitive pattern that goes over and over again. Why is it blue? Because it has some impurities in it, and that's what gives it the blue color. So it's a repeating pattern. It could be a molecule, it could be a formula unit. So it could be covalent, it could be ionic, right? It could even be metallic. They'll talk about metallic crystals because it's a highly regular arrangement of atoms in a repeating pattern. Even though we don't think of it as a crystal, it still is in that sense. So examples, an ionic solid. And again, whenever they want you to give examples of stuff, always think of the basics. Go for salt. When we have the salt, we have the Na and the Cl and the Na and the Cl. So we have the positive and the negative and the positive and the negative. So we could say NaCl here. Stop it.
Every time the microphone goes up, I feel like it's bird box.
It's my family. They think they're funny, so they'll go back and forth for a while and include me in the group chat.
Bird box. Wait.
Yeah, so.
Where they can't see. What? That movie where they can't see. Bird box? Yeah, it's bird box. Yeah. Every time it goes
I
up,
didn't see that.
reminds me of that. They're like, oh my God.
Okay, so you have this highly regular arrangement of these. So when they have you draw this, and this could very possibly be something that they'll have you draw, you need to understand that the negative ion is going to be bigger, right? And the positive ion's typically going to be smaller because it lost the electrons, right? Smaller, going to bring it in. You can have a molecular solid. That's a crystal, so it can be ionic, it can be molecular solid. And this would be like sugar crystals. Water, ice. Aren't those crystals? Snowflakes, yeah. You can have an atomic solid where it's not a compound of any kind, it's just a pure atom. And you could think of, do you guys remember, okay, so do you remember a lab we did where we had the little bitty, hang on, my brain just lost the word. So we had these little wells, the little plastic that had the little wells in it, and we put oil in one, we put water in the other, and then we put stuff in them to see if they dissolve. Really? You don't remember? Yeah. One was this really bright orange crystal, little bright orange. One was iodine, the little purple one, the one that was in the petri dish that made the dish purplish in there. Yeah. Iodine is an example of that. It's if you look at it, it looks like a purple crystal. It's atomic. It's a pure element, but it looks like a purple crystal. And then when it sublimates, changes directly to a gas, it turns like this purpley gas. And then when it hits onto something and changes back into, it deposits, changes back into a solid. If it's in the container, you can see it kind of a purple haze all over it. But if I let it out of that little container, like in where it combines with the air, it'll actually chemically react with some of the oxygen in the air, and it turns kind of this brown color. So I have this can, it looks like a paint can, and it's full of kitty litter, and that's what I put the iodine bottle in, and then I cover it up with kitty litter. It's in a plastic bag, cover it up and put it in there. And if you go in the storage cabinet where it is, all around it there's this brownish dirty dust all around it where I can't keep that from sublimating, so it gets out of the container even then. So it's an atomic solid, and we have iodine crystals. You have lots of things. Think diamond, and we can have, diamond's a little bit more complex than that, but still we can kind of think of it there. Yeah, so this is called what we call a crystal. The second one is called an amorphous shape. Amorphous I always think of it as blob shape. There's no pattern. It's disorganized. It's a disorganized arrangement. A great example of that is plastic. And there are lots of different types of plastics. You guys know that not all plastics are the same, right? So some people are stupid enough that when they store a chemical like, they made some hydrochloric acid, like 1 molar solution, and they want to store it, so they had this old soda bottle, they cleaned it out and they put it in a soda bottle. That's not going to work. It'll work for a very short amount of time, and then the bottle will start leaking acid all over the place, because not all plastics are the same. That plastic usually has a name for it on the bottom, so some kind of designation on it. Let me see if I can find it on here. It'll have letters like HDPE or HDP, or where is it on here? Should have a symbol on here somewhere. I'll have to look for it and find it. Really, I can't believe I can't find it. Anyway, I have a list pasted to the door in the chem storage cabinet that tells me what plastic is okay to put chemicals in. So we don't use soda bottles because it's cheap plastic and it's not made to last for the longest amount of time. I mean, if you talk about putting it in a landfill, yeah, it's going to last a while, but when you put chemicals in it, that's not a good thing at all. So you never store chemicals. Don't use soda bottles to store chemicals at home or anything like that. It's a bad, bad, bad idea. So amorphous are plastics, and different plastics are different thicknesses, they're different toughnesses, so you have to look and see what plastics are good for. But all of them are amorphous. There's no crystal structure in the plastics at all. The next one would be a network covalent. And I think we talked about this on your other notes. Network covalent, it's got the same bonding in all directions. This would be your diamond. Or if not all, then multiple directions. So some network covalent bondings are stronger than others. So this would be something like diamond, where it's all carbon. Graphite is weird. It's kind of half and half, because graphite will be bonded kind of like in the x-axis. It'll be bonded strongly in the x-axis, if you think about it like that. But then in the y-axis, where it's one on top of the other, they'll be light bonding. So they can slide and move easily across each other. So when you take graphite, you can see that it's not nearly as strong. It's not nearly as strong, so you can easily break it and put it onto paper, because it's network bonding, but it's not solidly network bonding all the way through. So it's an interesting one. Makes it really useful to us because it's like that. And then you have number 4, you have metallic alloys. Sometimes they'll call them crystals. I've noticed every once in a while on the AP test they'll talk about metal crystals. So sometimes they'll call them metal crystals. I don't like that. I don't know why, I just don't. In this case, again, you have the same bonding in all directions. Really strong. But it's going to be between metals. So here you have these between covalently bonded substances, atoms or molecules. Here you have them between metallic stuff. It could be the same metal all the way through, or it could be, since they use the word alloy, they're going to have another metal mixed in with that. Okay, so we had solids up here. I'm going to put a box up here. And then let's do a little drop down here for liquids, because, yeah, we can. So here we have liquids. And liquids, there's very little density difference between the solid and the liquid of something. In the vast majority of things, most substances show little difference in density. Just a little bit, but not much. It's the gas where the big difference in density pops up. Now, there's enough that you can tell, and the easiest one, the one we have the most access to, is water. So when we have solid water and we put it into liquid water, which is more dense? Which one floats? The solid floats, right? That's abnormal. Water is the only one that does that. Every other substance on the planet, if you have the solid substance and you have the liquid substance, when you put the solid into the liquid, it sinks down to the bottom. Okay, hang on. I'll wait for you guys to catch up and we'll try this again. Okay, let me say that again. Water's weird. Typically, there's not a whole lot of difference between the solid form of something and the liquid form of something. The solid's usually slightly denser, so when you take a solid chunk of it and put it in a melted liquid stuff, it'll sink to the bottom, except water. Water's crazy weird, and because it's crazy weird like that, we have life on this planet. Because remember, because the solid form of water is less dense than the liquid, a pond or a lake doesn't freeze from the bottom up, where if it's solid it sinks to the bottom. It freezes from the top down. So what that allows is it allows a layer of liquid water to stay in there so organisms can be alive in that liquid water below that top solid water that's up there. That's hugely important. Most ponds and lakes don't completely freeze over. I mean, they're usually too deep for that. The most ones that are stable lakes that stay there for a long time, then they're too deep for that, and so they have a place down towards the bottom where the life can survive down in there. Yep. So water is strange. You know, it's not normal like other stuff. And the reason that the solid water is less dense is because it forms a hexagon. So when it starts to when it starts to freeze, because of the intermolecular forces, the hydrogen bonding, they freeze into a crystal little hexagon shape, and there's an air bubble in here. There's oxygen in there. So that's what makes it less dense. That's the way it works. Can you compress it? Yeah, you can compress it, but it's still going to have this basic form here. Yeah. So in most cases, again, the solid's going to be just a little bit more dense. And we don't typically see solid forms. For most things, we don't see both the solid and the liquid form of it, do we? I mean, we just don't. We have it at room temperature. Either it's a solid or a liquid at room temperature or a gas. So we don't typically see both. Water's the one where we see both. We can even see all three of them, right? Solid, liquid, and gas on there. Yeah. So most of the substances, there's not a big difference in density, but in water there is here a significant difference, and it's different from everything else. So we can look at a couple of things here. Let's look at the word viscosity. Viscosity is a resistance to a flow. Let's put it that way. Resistance to flow. So water is not viscous. It flows pretty easily, doesn't it? That's a yes/no question.
Yes.
Yes, it does. So water's not very viscous. So viscosity is that resistance to flow. The bigger and longer molecules tend to get tangled up with each other when they try to flow, and that's what makes them more viscous. Not vicious, viscous. A lot of times we think thick. Now, the other thing that can make it more viscous is more IMFs. Typically means more viscous. Again, this one doesn't give us a good idea with water, because water has those hydrogen bonding. But in general, it's this that's the most important. So I'm going to put this last little piece in there. I'm going to put it in parentheses. What's most important for viscosity is how big those molecules are. They get all tangled up. Think of it like spaghetti noodles. Yeah, think of how tangled they are. When you have bigger, longer molecules, they get tangled up with each other and it makes them thicker. Think syrup. Syrup is viscous, yes? If you heat the syrup up, you actually expand the molecules. You get the molecules expanded a little bit. They get a little bit less tangled,
Like
and so
peanut
it's
butter.
more runny. Yeah. Yeah. The next thing we're going to talk about here with liquids is surface tension, which again we've talked about before. You can if you want. I don't have anything on there. Yep, so if you need more space, you can. Surface tension, this is the attraction of molecules to each other. on the surface of a liquid. Will you stop that? I'm going to put this on the surface of the liquid. Attraction of molecules to each other. And because they're attracted to each other, it almost forms like a skin on the top of on the surface of a liquid. Okay, so I'm going to turn this paper sideways a second here. So here is a drop of water. Okay, there's a drop of water. And you guys know it beads up. When you put water on something, it beads up. That's crazy that it's so attracted to each other. So water molecules are attracted to each other, attracted to the ones below it, right? And then they're also attracted to the ones beside it, right? So that's an arrow there that didn't come out right. So they're attracted to each other and the ones beside it. When you have it on the surface, there's nothing up here for it to be attracted to right out here. So they're strongly attracted to each other on the surface and they pull themselves in. So when you have a barrier, here's the water, and then there's something else, air, the water molecules are attracted to each other. And so it forms this kind of skin on the top that we can take that paper clip and set it on top of there. So when you look at that surface tension of something, it's all about cohesion. Cohesion is attraction to self. I have this stuff called Gorilla Tape at home. Coolest stuff ever. Gorilla Tape. I can peel it off. Doesn't stick to me, doesn't stick to anything at all. It only sticks to itself. So I have a hose coming out of my pool that sprung a leak, and I didn't have a hose to replace it with, and so I grabbed my Gorilla Tape and I wrapped it around the hose, and then I wrapped it around itself, and it stuck to itself and formed an airtight seal. So that happened early on in the summer. And so it stayed that way all summer long until I took it down. But it's cohesive tape. What we have here, most tape that we use is adhesive tape. Adhesive tape is attracted to other things too. Not just itself, although I can stick these two together. It's attracted to a lot of other stuff. So cohesive means together, it adheres to itself. Okay, the next one is capillary action. How much time do I have left? Crap. Okay, capillary action. Capillary action is when it's attraction of molecules of a liquid to the sides of a container. Attraction of molecules of a liquid to the sides of the container. And when I say the container, it's a tiny tube called a capillary. When we say the word capillary, we're talking tiny tube. This is adhesion. And that's attraction to other stuff. We've talked about capillary action. So we can prick your finger and get this little bitty tiny glass straw and stick it in the blood drop and it'll go all the way up. They can use that to determine how quickly your blood clots. Naturally, we can take the edge of a paper towel and stick it in a drop of water and that water's going to soak all the way up. That's capillary action. We can take plants, can get water from the roots, and through capillary action, they don't have any muscles to push it up there. Capillary action takes the water all the way up to the leaves. So we have capillary action. Think paper towel. That's the best example I can give you guys because you all have access to that. And then last one, Oh, there's one more after this, sorry. There's no crystal. No crystal structure at all. And the reason I said that is because there was a question that said the crystal structure of this, or one of the possibilities was the crystal structure of the liquid. It's like, no, there is no crystal structure of a liquid. And then last one would be hardness. Hardness refers to, oh, that should have been up in the solid. What happened here? Hardness, okay, so I'm going to bring this back up here. Are you ready? Yes or no? Okay, so I'm going to come back here. I forgot one up here. So number 5. Yeah, there are no crystals. Just make sure you know there are no crystals in liquids, right? They don't form a crystal structure. No, so number 5 up here, apparently I just skipped over that. Hardness. Hardness, we talked about the scratch test. How hard is it? CRATCH, scratch test. Did you guys study this Mohs hardness scale?
No, we're not.
Like, what's the hardest stuff we have? Diamond, right? And then we kind of go down from there. Mohs hardness scale is just a scale to test that. But hardness, we talk about the hardness of solids too. So sorry, I just flat out left that one out.
Wait, so what was Korean milk?
1, 2, 3, 4. No crystal structure. Hardness is just, you do it by a scratch test. Which one's harder? This substance or that substance? Chalk is not very hard, is it? Chalk and slate. Slate is harder than chalk. So the slate, when I write the chalk on it, the slate stays the way it is. It doesn't get scratched, and the chalk breaks off on there. Graphite. Graphite, look at this. Graphite is not as hard as paper, is it? Because when I write on the paper, the graphite breaks off and does that. So paper is harder than graphite. That would be something that we talk about with the Mohs hardness scale. So it's a series of showing you all the hardnesses on there. Which substance is hardest? Which is harder? Do you guys know opals and emeralds are not very hard? They break easily.